With no further ado, I will let Ewen Denney from NASA Ames, who was kindly to join here very early in the morning for him, deliver the keynote for this event. So, Ewen, when you're ready.
All right, thank you very much. And as I was just saying a minute ago, I'm afraid there's a possibility that my internet might die at some point during this talk. So just to let you know. All right, okay, so thank you very much for the invitation. I'm very sorry I wasn't able to hear any of the earlier talks. I mean, the program looked really fascinating. Maybe I'll see some of the slides or recordings of them later on. But I'm glad to have the invitation to talk about some of the work that we're doing with assurance cases. And Ulrich asked me to talk about some of the work we're doing in the area of tool support, and so I'll concentrate on that. But we're not just developing tools, we're actually applying the tools ourselves. So I'll also say a little bit about some of the applications that we're applying those tools to at NASA, and also throw in a little bit of sort of computer science, sort of foundational stuff as well. All right, so I'm going to give an introduction to the notion of assurance cases and safety cases, give some idea of how we apply this in terms of methodology, some basic concepts, a few applications that projects where we've applied this, and then, as I said, concentrate on the tool, and lastly, draw some conclusions. Hopefully stay within time. All right, so just to get started, I think it's kind of useful to say a few words about the history of the concept and also the wider regulatory framework. So it's actually an interesting time right now in the area of safety because different domains at different speeds are gradually moving in the same direction, I would say, although many of them use different names for the same thing. But overall, what's happening is that we're moving towards an era of active safety management. And this is sometimes encapsulated in the notion of a safety management system. And in a safety management system, what you do is you make safety first. It's the central thing within all of your decision making. And it's not just something that you do at design time, but you actually monitor and you update and you use to sort of govern your operations as you move on. So it actually governs the management of your system. And you can have all sorts of various structures in place and kind of legal and actually computational structures in place to manage these things. But at a high level, that's kind of the idea. The safety management is central to how you govern your operations. A similar concept, not exactly the same, but actually very closely related, is goal-based regulation. And again, this is something, a trend that we've seen over the last decade or two, actually, in various different industries. And goals-based regulation, also known as performance-based regulation or product-based regulation, is an alternative to process-based regulation, which is the traditional way of getting approval for some operation or product to go into practice. And in process-based regulation, what you typically do is you follow a particular process and you supply certain data, you do certain analyses, and then you get a stamp of approval. And the implication is that somebody has developed these regulations in such a way that if you follow the process, the implication is presumably that your product is actually meets certain kind of safety or performance criteria. But an alternative to that is to not follow any prescribed process, but instead to just analyze the product itself, identify certain goals and show that you meet those goals using whatever techniques you can bring to bear. And this is an attractive approach to follow when the regulations themselves are in flux and performance standards have not yet been finalized or indeed absent. And this is the case actually with UAS, unmanned aircraft systems, drones, and also with many applications of autonomous systems. Self-driving cars come to mind. Many companies actually like this approach, not all, but many like it because it provides additional flexibility. You don't have to follow a particular approach to show that your system is safe. You can apply whatever techniques you think is appropriate. Of course, this places a greater burden on the regulators because now they have to be able to understand whatever techniques the practitioners throw at them. But anyway, that's kind of the trade-off here. And generally, the end product of all of this, the thing that you produce in order to justify that your system is safe or meets its performance criteria, is called a safety case. And so that's going to be the focus of the talk today. Now, there's many different definitions here of what a safety case is, or more generally an assurance case is. And I'll give a few quotes here. Oops, I need to move something out of the way. All right. So the NASA System Safety Handbook, there's 2 system safety handbooks from NASA, provide a kind of very nice and quite detailed description of NASA's concept of what a safety case is. It's defined there. I need to minimize some Zoom participants here. Give me a second. A safety case is a structured argument supported by a body of evidence that provides a compelling, comprehensible, and valid case that a system is safe for a given application in a given operating environment. And we see here several features of the safety case concept. One is an emphasis on convincing people. So it's got to be compelling, comprehensible, and valid. Another is that you're talking about the system for a particular application. It's not independent of how you're using the system. So it's a particular environment. And also each of these definitions talks about the argument as being a central thing. So rationale, justifying why something is the case. I won't dwell on the other two definitions, which are kind of similar, and there's many other ones besides. I'll just mention the last point here. There's that originally safety cases were this sort of the initial idea here, but over the years people have generalized this to other properties such as dependability properties in general, security in particular, and this more general notion is called an assurance case. And so we'll tend to use these two things synonymously: safety case and assurance case. Safety case is the more common one, it's the one people tend to focus on, but assurance case is a more general idea. All right, so the safety case then, or the assurance case in general, is as I said when I mentioned the notion of safety management systems, is a safety risk management artifact which you should use to sort of govern the operations of your system. It's not something you do at design time and then throw it away. However, it should serve as an authoritative record that you've done due diligence, you've identified all of the safety risks, that you understand them, and that you've put in place mechanisms and processes for maintaining and reducing those risks to an acceptable level. And this should be something that you do as you're designing the system. So it should be a driver for the development of the system itself, not something you do after the fact, but it should also be something that actually itself forms part of the system and is actually actively used in the sort of the management and the operations of the system. Mentioned that argumentation is a key part of this, and that the purpose of the assurance case is to assure. Now, just one subtlety of the words here in English that many English speakers actually often don't quite get is that you ensure a fact, you ensure that something holds, but you assure a person. And the reason we call them assurance cases and not insurance cases is that you are assuring a stakeholder, you are assuring a regulator that something holds. And this is very important. This means that an assurance case is fundamentally a communicative artifact. It's something to communicate to the regulator why your system meets whatever goals you want to put about it. And hence, it needs to be compelling, convincing, and so on. All right. Personally, I think it's quite interesting and insightful to step back and look at the history of some of the concepts that have led us to this modern notion of safety cases. So I'd like to spend a little bit of time giving, at least from my own perspective, what I see as being some of sort of the sort of road marks, milestones along the way here, and perhaps this is a bit biased to my own sort of background. I've got a few here from my native Scotland here, but I think actually these are some of the key sort of things that have happened over the years. So in 1871, there was a very famous rail disaster in Scotland. A railway, a train was crossing a bridge just south of Dundee. The bridge collapsed in bad weather. Nearly 100 people died, and there was a big inquiry. And so far as I know, this was one of the first ever formal accident inquiries that led to, some kind of quite a comprehensive inquiry actually. Lots of sort of very sophisticated sort of engineering analysis went on. Unfortunately, they didn't decide in advance what the actual purpose of the inquiry was. So there was a lot of squabbling and legal wrangling and so on. So that was a bit unfortunate. But nevertheless, that was the start of at least one of the very first formal accident inquiries. Then jump forward about 80 years to England now, and there was an accident in a coal mine where the coal face collapsed and a miner died, and then they had an inquiry into that, and the coal mine argued that, well, really there was nothing they could have done. Unfortunately, these things happen, and it would have been far too expensive to, I don't know, put in supports to stop the miners being killed. And, understandably, not everybody agreed with that. But nevertheless, it raised an uncomfortable but important point, which many people don't like to think about, but is unfortunately absolutely a fact of life, which is that you do have to draw the line and you can't spend infinite amount of resources. And this led to the introduction into law of the concept of as low as reasonably practicable. And this goes by different names and nowadays in different safety standards in different countries in the world. But essentially, this is the idea of your risk mitigations being commensurate to the level of risk. Your bang for your buck. You spend what is considered to be reasonable, where there's some, arguing about what reasonable means. But nevertheless, this concept then came into law. In 1974, there was the Health and Safety Work Act, and here we start to see some of the more modern concepts of goal-setting regulations coming into play. So instead of following specific principles, instead of ticking boxes and saying, I've done this and I've that and the other thing, instead figuring out what are your high-level safety goals and saying that the purpose is to meet those goals and do this however you want. Then in the 80s, 1984, there was an accident in a chemical plant in Italy, I think it was. And this led to more specific notions of formal safety assessment in the EU, safety, hazard assessment processes, risk mitigations, and so on being codified into law. This was updated in 1999. And then sometimes what's considered as being sort of the thing that was the spur to the modern notion of safety case was the Piper Alpha accident, again in Scotland in 1990. I don't know, 200, maybe 300 men died in the North Sea, terrible disaster. And there was an inquiry after this, and basically, to cut a long story short, the government inquiry led to the recommendation that safety cases be adopted in sort of all sort of offshore, that is, in oil and gas installations in the North Sea. And then lastly, 2004, the UK Ministry of Defence now from 2004 required safety cases with that definition for any for all contracts. All right, so that's some kind of points along the way that's led to the sort of modern concept of safety cases. And the idea then of the safety case is that you, as I said, you want to convince, you want to capture rationale, and there's many kinds of rationale that you would want to capture in a safety case. Just some examples here. So you want to show how your high-level goals or your assurance objectives can be decomposed into lower-level claims. You've got various forms of verification that you're doing, and this could be formal or informal verification, simulation, expert analysis. And you want to show that that verification is appropriate to what you're trying to do, that you're relevant, that your evidence is relevant, and that the various analyses you've carried out are comprehensive. And often this can't be done in a formal kind of sense, but there's nevertheless usually a compelling argument you can make for why you believe this to be the case. One key thing that you often is a good idea to do is to explicitly address counter arguments. What are reasons why you might have reason to doubt that your system is safe or meets its goals? Address those head on and say why you've thought about those things and you've addressed those. You typically will have a number of risk mitigations in place, and sometimes it's important to show that those are independent of each other. Again, can be quite hard to reason about formally, and often you'll have an informal argument for this. So all of these kind of things are things that often will form key parts of an assurance case. All right, and as I said, in modern times, this is being gradually adopted in a range of different industries. You sort of read some of these here. I'll just mention some that I've not mentioned already. The FAA is the United States Civil Aviation Authority. I was in a talk just a month ago and was quite amazed to see that they're moving now towards performance-based regulation. And they didn't use the word safety case in the talk. Instead, they said that they're going to rewrite all the regulations to be performance-based regulation. But afterwards, I asked the speaker, well, and how would you go about showing that you meet these performance-based regulations? And he said, oh, with a safety case. And I can give you a kind of a somewhat comical example of what the man from the FAA gave as an example of performance-based regulation. He said that the current law is that all of the aircraft, Boeing and Airbus, I guess, have to meet certain regulations that say that you can, in the event of an emergency, that you can sort of get out the emergency exits within a certain amount of time or so on. But in actual fact, that's not what the regulation says. What the regulation says right now is that the windows have to be a certain dimension, and the doors have to be a certain dimension, and it goes into great detail about all of these sizes. And the trouble is that Americans are getting fatter and they can't actually fit out the door anymore. So the bottom line is that they have to keep updating the regulations to sort of address the sort of increasing size of Americans, not just Americans, many people. So instead, now what the regulations are going to say is that you basically have to assure that people can get out the door in an emergency within a certain amount of time, and that will remain fixed. So waist sizes might increase, but the amount of time to get out is going to be invariant. So I thought that was kind of a funny example of a performance-based regulation. Okay, more recently in the automotive domain, there's a lot of interest in safety cases. The ISO 26262 standard recommends them, or requires them rather, for functional safety. And then there's very interesting things happening in the autonomous space. All right, let me move on. Okay, so many advantages to assurance cases. I'll press on, skip over some of this. So methodologically, the way in which you create assurance cases then is essentially you identify your hazards, you ascribe risk to them, you identify your risk controls, you develop requirements to implement those risk controls, and then you monitor those in practice. And safety assurance is actually the FAA's term for monitoring the effectiveness of your risk mitigations in practice. And within our work, we use various modeling formalisms for these. So we have a particular habit representation, a particular safety model for representing risk and requirements. We use barrier models in the form of bow tie diagrams for identifying our risk scenarios. And then we use the goal structuring notation for providing rationale for our assurance arguments. And I'm going to say a little bit about these two modeling notations because they are essentially the core of the assurance case. And I'll try and speed up here. All right. Okay, so concepts. Okay, so as I said, the assurance arguments and the what we call the safety architecture, which is these barrier models, along with the hazard analysis from the core of the safety case. All right, so goal structuring notation is a graphical notation for step-by-step development of assurance arguments or rationale. And sometimes I prefer to call them rationale rather than arguments. We had a man from the FAA visit this one time, and we were talking to him about arguments, and he got the idea that arguments is all about guys like punching each other in the face and so on. But sometimes I call this rationale. And the idea here is that these square boxes here, you provide goals or claims about your system, and these parallelograms are strategies, so reasoning or inference steps where you decompose the high-level claims into lower-level claims or sub-goals. And you do this recursively until you eventually reach a low enough level where you can provide a solution or evidence, such as verification, that shows that you meet your goals. Very, very simple idea. And you can think of this as essentially being an informal proof. And there's certain kinds of auxiliary nodes on the right here to provide additional contextual information and justification and assumptions of why you're doing it. But essentially the core of it is this step-by-step decomposition here. And this is a very, very simple idea, but nevertheless, it's something that is often left very implicit in informal safety assessments. And often it requires a lot of thought to tease out. And often you find that there's gaps in the reasoning that requires a lot of thought to bring out. So it's kind of very kind of useful exercise to identify these things. And here's an example that I'm going to be providing later on of an argument that we've created here. And what this is showing is that a radar that we were using for detecting intruders into an airspace where we were conducting operations for our drones is essentially able to perform its function. So the ground-based surveillance capability is adequately able to detect aircraft in a particular airspace. And then these contextual nodes here, we sort of provide additional information about some of the terms here. And then we gradually decompose over various aspects of the system. In this particular case, on the left here, we're looking at aspects of the physical system. So there's the telemetry, the transponders, and so on. And on the right here, we're looking at the various procedures that are being followed in using that equipment. And this illustrates one of the features of assurance cases, which is that they're at the system level, and that also they're highly heterogeneous. You need to consider the system, the procedures that are being followed, all of the participants in that system. So it's not just you're looking at a piece of software or even a piece of physical hardware in isolation. It's the system in conjunction with all of the participants, so sometimes called system of systems. All right. In practice, those things go very large, and so we want to introduce structuring mechanisms. I won't dwell on sort of the computer science aspects of the distinction between modularity and hierarchy, but these are two different structuring mechanisms that we can bring to bear. And so we can structure these students' cases in a hierarchical way, just chunking them up like that, and also in a modular way, so sort of structuring them like that. All right, barrier models. So a barrier model is a scenario-based event chain model of risk. And the idea is that you're essentially looking at all of the possible causes that can lead to bad things happening. And a bad thing happening is when you lose control. But bad is sort of relative in the world of safety, because bad things can lead to even worse things. And so typically you have these really, really bad things happening. This will be an accident happening. Somebody dies or has an accident, or you lose your drone or whatever. And that's too late. So really the thing you want to focus on is when you start to lose control. And in the world of barrier modeling, you call this the hazard. And then what you do is, well, you say, well, what are all the possible threats? What are all the possible causes for why I might lose control? And you identify each of those. And then you say, well, how can I prevent those threats leading to me losing control? And you place barriers in the way of the threats and the loss of control. And these are prevention barriers. Now, if this really bad thing does happen and you do lose control, how can I then recover from this and prevent this leading to the very, very bad thing happening? And those are recovery barriers. This is a very useful way of thinking about safety. It's a very useful way of architecting your safety system.
Ewen, I think we lost your audio for a while there. Are you still with us? Damn it. Let's just give him a moment to reconnect. Ewen, if you're still speaking, we can't hear you. All right, he jumped out of the meeting now. Let's see if he reconnects.
I'm communicating with him via his mobile phone. He's trying to reconnect.
Okay. I expect everyone to be able to give a full recap on the last 3 slides that he presented, each of the boxes.
So I'm still in contact with him, and he's fighting with his, of course, as everyone else, he's stuck home. And unfortunately, he's stuck home with an internet connection that's been unstable since yesterday, and apparently still is stable this morning.
If you're wondering where I went, I have some issues with my camera as well, so it just turns out to be yellow circle apparently.
Okay, so we're going to try a desperate solution here. I have Ewen Denney via Google Hangouts connected to my screen, and I have his slides in PDF. And I'm going to try and have the two side by side and then share my screen.
All right.
Yeah, and I hope this works, and I should be able to, just a second. Could you make me, Eske, could you make me, can I share my screen? Yes,
I think you can.
Just a second. All right, I'm now sharing desktop with Ewen, and I'm sharing my sound as well. Ewen, could you try saying something?
Yes.
Okay.
You can hear me fine, all right?
And people, can people hear him through Zoom as well?
Yes. Yeah.
Okay, you're good. You just tell me which slide to go to.
All right, we're on the example multi-diagram, lots of separation.
If we can get maybe a bit more volume, that would be nice. But if not, then okay.
Yeah, but loss. Okay, here we have bow tie diagram, loss of separation. That's slide 25. Okay, volume is a bit low. That's an issue with this setup.
Okay.
But I don't think I can fix it.
Okay. All right. Well, anyway, I'll keep going. So, what I was saying was that here's an example of a bow tie diagram, and an interesting thing is that essentially what you do is you consider bow tie diagrams your barriers. So, for example, we see here that the emergence procedures are one of the mitigations or barrier mitigation. It's the same thing for this particular threat. And what I then do is I consider, well, now what are all the possible reasons why that particular barrier might be compromised? So then, so this is the particular mitigation. All right, so next slide, please, Ulrich.
So safety architecture. So actually, Ewan, the connection is really bad, actually. Can you, what if you cut your video to reduce your bandwidth? Okay, now just keep talking. Yeah, go on. So this is the safety architecture slide, right?
All right, and the safety architecture. So the architecture is within your system, and this provides a picture of the safety that's called safety architecture. And tools, of course, very important to make sure that each of the different mitigations have playwright. Step over to the examples.
Okay, examples. We are now at US traffic management.
So for another UTM system, that's the US traffic management. I know similar things are underway in Europe and including in Denmark. And next slide over.
Okay, factors affecting.
So, there are many kind of many different safety considerations in place here. Actually, next slide over. Concept of operation.
Yes.
And so this was about halfway through the UTM project, and this was going to be the first time they were going to conduct operations beyond visual line of sight. And this was a key step. Up to that point, we had never done beyond visual line of sight operations of drones in the national airspace in the US. So that is, beyond, out of physical sight of the operator of the drone. And so the FAA required
operations that were in place. Next slide over.
BVLOS safety.
So anyway, many safety considerations there. So next slide.
Safety concept.
So we use basically ground-based radar in order to ensure safety. We had to reason about the geometric configuration of the radar operated, any mitigations that were in place, analysis. Next slide over. And essentially, we created a safety case for this using our tool. And so this was the first time ever that BVLOS operations had been approved in the US, and indeed this was done using a safety case. So the FAA followed up with us and wanted many additional briefings and safety cases and whatnot. And so we think this was kind of a kind of seminal moment in sort of the modern history of safety. Next slide, Ulrich.
Barrier fitness.
Over the next couple.
Okay, so
show this example,
yeah. Requirements implementation.
This one, yes, okay, requirements implementation. So an important part of the safety case then is to not just reason about the safety of a system, but to actually play a role in the design of that system. And this is where the requirements come in place. Now, the table you the separation limits. And there's many different separation limits you need to take into account when you're doing your drone operations, vertical, lateral, and so on, and you can see some of the examples there. So we had to reason about all these different separation limits. And so actually, in the course of this safety analysis, we were actually designing the mission in effect. And so the requirements design is actually a very important part of the safety analysis. Next slide, over.
Runways in the line.
All right, I think I will skip over this example. This is actually an autonomous application here, more recent, using about kind of a neural net. So let's skip over that.
Okay, assurance argument architecture.
Yes, tool support.
Tool support. Okay, tool support. Yes, advocate.
All right, so advocate is the tool that we use for and the one thing I have to remind my boss is that the creation of a safety case is not a push button thing. It's a tool for people to sit down and do careful thought about designing a safety case. So safety cases are written by people, they're not created by tools. But nevertheless, the tool is sort of there to help us do our job. And you see there many of the capabilities that it has. I'll skip over the next couple of slides. There's some standard things. Skip over to argument patterns, Ulrich, please.
Yes.
So argument patterns are a high-level encapsulation of principles of reasoning. They're an abstraction of a student's arguments. Next slide.
Atomic patterns.
We can define atomic patterns. We can compose these patterns to form more complex patterns. Next slide. Pattern instantiation. And we can then automatically instantiate these patterns to provide arguments. And this methodology essentially is analogous to trends underway that have been underway for a while in model-based systems engineering. We're raising the level of abstraction. And so then the creation of these students' cases, the identification of high-level principles of reasoning, these patterns, and also the data, the underlying evidence that you use to plug into those reasoning principles. So it's kind of a two-step process that we're recommending. Okay. Next step. Next slide, please.
Round tripping.
Yes. And so you can then, of course, ask yourself questions. Well, if I modify my generated argument, does this translate back to my my high-level thing? Safety engineers call this round-trip engineering. Your scientists call this bidirectional transformation. So you can consider various scenarios where you propagate changes back and forth. So we support all of those. Lots of interesting things to do there. Next.
Tracing consistency.
Over the next few slides, they just eye candy on various features of the tool. A student's dashboard. We have support for workflows. Ontologies, all right.
Yeah.
So we also allow people to use ontologies to provide domain models. So this is a semi-formal modeling language providing additional information on top of the sort of core modeling concepts. In the bottom right, you see a fragment of an ontology we developed for an autonomous underwater vehicle. So it defines fins, their components, degraded modes, and so on. Next slide, Ulrich. So this gives a view of we can use these to define ontology enhanced assurance cases, and then do various kinds of interesting analyses. Next slide, please, Ulrich. Queries and metrics. So we have a family of languages that we can then use to analyze the student's case in various ways. So on the left, what you see there is a couple of queries and also metrics for analyzing the student's case. So the formal language is on the right, so the tool can analyze these things and give you various insights into your student's case. Next slide. All right.
Tables and views.
Yeah, so the queries can also be used to define tabular representations. So many people, particularly at NASA, love their Excel spreadsheets. And so we can actually use the model to generate tabular representations of the student's information. And just a very simple example there. And also graphical representations. I don't have an example here, but we also have graphical views that we can use the same language for. Next slide, all right.
Dynamic, static.
So traditionally, student cases have been thought of as static things, and this has actually been an unfair criticism, in my opinion, of them. But nevertheless, there is a challenge to ask about how you update a student's cases at various sort of temporal horizons, designed at runtime, at operations, between missions, and so on. And so this has led to the concept of a dynamic student's case. And so we're looking into this. Next slide. And the idea here is, so this is the dynamic assurance concept, and the idea here is that you can think of an assurance case as serving two roles. So although I, in my initial few slides, sort of tried to motivate that an assurance case, the primary purpose of an assurance case is to communicate to a human being that your system is safe. In practice, actually, what you can do is you can compile off certain executable fragments of your assurance case and use these in operations. And we call these assurance measures. And we have a whole theory about these that I won't get into today. And these assurance measures can provide a notion of confidence in the operation of your system that is then consumed by a runtime decision mechanism. And so what you see here is a kind of operational concept for compiling assurance cases in practice. And this is particularly useful for autonomous systems. And we're exploring this concept right now, and we've instantiated it in a particular aircraft, an autonomous aircraft. And you see here a particular instantiation of that concept. I'd say much more about that if I had time. All right, next slide, please.
Architecture.
And yes, and going along with that, we have a dynamic dashboard, which is providing some insight to the operators of the autonomous system. So, you all know that, of course, an autonomous system is only semi-autonomous. It still has people who are operating it. So always a degree of autonomy. So this provides various kind of insights from the compiled assurance case into the state of confidence in the particular machine learning component that is being used in this case to taxi along the runway. All right. Next slide, Ulrich.
Dynamic.
This should be my conclusion slide.
Okay. Yes.
Yes. All right. So I'm sorry there. I had to really rush through the talk to get to this point more or less on time. But maybe I can spend a little bit more time to sort of dwell on my conclusions here. So so I think there's two important themes in ongoing research, our own research, but also the community at large in assurance right now. And one is the need for integration of design time assurance techniques and operation time assurance techniques. And just 10 minutes before I gave the talk, I made up Dev Assurance Ops, since I've been reading a lot about DevOps lately, and it seems like a cool thing to get money from funding agencies, so I don't know. But anyway, it's basically DevOps for assurance is really the idea here. And we have ideas for how to go about doing that, but it's absolutely, there's lots more work to be done there. And another theme that we are tackling is raising the level of abstraction at which you're doing assurance. And this is a thing that's undergoing in sort of many areas of computer science and engineering in general, model-based, this, that, and the other. And so, we believe that this is going to lead to better scope for reuse and actually, ultimately for safety. Okay, and so I raced through various sort of core assurance case concepts and some of the more advanced ones just at the end there, to do with automation, ontologies, and queries using metrics that I didn't have too much time to cover. Over the years in developed about 6 or 7 assurance cases, and I just gave a couple insights from a couple there. Now, we've kind of had a few conclusions that we've drawn. And one is that, people really don't care about notations all that much. In fact, many of the applications that academic researchers are most fond of, practitioners actually couldn't care less about and really actually kind of a disliking for. And really, the whole purpose of the assurance case is to assure. You have to come back to this fundamental point that the point is of the assurance case is to convince the regulators or whoever the stakeholders should be. And it's very important to initiate a dialogue with them very early on and understand what it is they're looking for, what is it they want to see, and what is it that they don't want to see. So that maybe is kind of an obvious thing, but I think it's a lesson that many researchers have not yet learned, actually. And another lesson that I would say that actually many researchers haven't got is the importance of methodology. It's no good having a tool, for example, the world's greatest static analysis tool, if you don't explain how to use it and when to apply it. And I think many of my colleagues actually are guilty of this. I often ask them, can you explain to me what your tool is good for, when you can use it and all the rest of it, and they can point me to all these papers and great theorems, but they really kind of have no idea about what the methodological aspect of that. And that is very important, and actually a bit of work. There's actually a lot of work to do there. And the last point I want to make is that it's very important to develop a system along with the safety case, because a large part of the safety case is actually designing the system itself. All right. So on the right here, series of bullets, several sort of ongoing themes of work that we're looking at. One is alternative risk model. Although I didn't really touch upon the risk model that underlies the work that we've described here, it's a traditional severity versus likelihood risk model. But there are other ways of characterizing the notion of risk. And in the automotive domain, in ISO 26262, people talk about severity, exposure, and actually controllability. And this is kind of a different way of thinking about risk, but an entirely legitimate kind of one. And so, we need to think through, well, what is the implications of that for the overall safety process, having a different risk model. Another thing we would like to do is streamline the overall process. So I maybe overwhelmed you with too many things in this overly compressed talk, but I think really what practitioners want, so for example, robotics practitioners, they want a robotics tool. They don't want a safety case tool. They want a tool that will help you reason about the safety of your robots. And so really what you want then is a library of assurance artifacts specific to your domain, templates of reasoning that are applicable to robots, domain concepts, perhaps if you're interested in ontology, sort of fragments of domain theories that are relevant to robots. And one way that you could perhaps think about this is as a product line. And that may not be the most useful way, but that is one way. And this is sort of in the spirit of what's going on right now in the drone world with SORA, which is customizing and streamlining and encapsulating a lot of the sort of basic safety reasoning into a very sort of simple process, which is a nice idea. And so similar things could perhaps be done for robotics. And another is taking serious the notion of workflow and allowing people to customize workflow to their particular domain. Okay, another interesting thing that we want to do, in fact, in collaboration with Danish researchers, is look at connections with simulation. So there are very interesting connections that can be made between the models which underlie insurance and the models which are used for simulation. And for example, what you could do is you can actually simulate some of the bow tie diagrams that you have that provide you risk scenarios to insight into your safety system. One thing I didn't talk about is quantification of risk. We can use the risk model to assign numbers to the hazards, in other words, to get likelihoods. And it's always a great challenge to come up with these numbers. Now, we could use these simulation models to actually provide a good first cut of these numbers. So it looks like there's kind of potentially very useful connections in both directions in the world of assurance and the world of simulation that I think are very much worth exploring. And hopefully, when coronavirus is over, we'll be able to explore those in person. Lots more scope for automation. So we're interested in sort of automating many of the hazard analysis and also synthesizing fragments of the argument. The ontology will be very, very useful there. And also for moving in the direction of consistency checking using more structured languages. So I don't recommend going for full formal languages. I think that's not the purpose of assurance cases, but we can certainly move towards more structured natural languages where underlying those there's a sort of rigorous basis grounded in ontology, and we can actually do a lot of consistency checking there that would be very, very useful without annoying people with formal languages. And lastly, there's a lot of work to be done in sort of integration with all sorts of other tools. So engineers are familiar with various kind requirements engineering tools. There's also a lot of interesting work that can be done with sort of Bayesian reasoning that we want to integrate with, and formal methods as well. I would think of these things as being sort of external tools, but a lot of interesting thought can be done to integrate these with the overall assurance process. Okay, so I'm sorry I kind of slightly went over time. I just came across this interesting example of Danish technology that NASA is currently testing in space from the NASA archive. So I just wanted to sort of show you that exciting example of Danish technology there in space. So thank you very much. Sorry for the connection problems. Back to you, Ulrich.
Yeah, thanks, Ewen. Thanks a lot. So I don't know, do we have time for if there are any questions to Ewen? I can try and route them to him. And
Sure.
yeah, I think people should, at this point it's utter complete chaos, so I think you should just unmute and say something if you want to ask something to Ewen, and then I can try and repeat it to him. Maybe Ewen, actually something that was on my mind. I don't know. I mean, this is sort of a. I'm not sure if this is actually a useful question or not. But is there? I'm on your thank you slide. Yes. Yeah. So, but is there any way to? I mean, how much do you gain from the tooling, and can you quantify that in any way, or is it just that people like to use the tool?
You know, people are always asking for this quantification question.
Yeah.
It's extremely difficult, Robert.
I know.
I mean,
sorry for asking.
I can answer the question of how much do you gain. I mean, I have no doubt that the tooling helps because, you know, we have created assurance cases ourselves, right? And so we know how much work it is to do this. And the biggest difficulty is just keeping everything consistent. So you have a table of requirements. You have a table of your safety mitigation somewhere in the report. And it was just constant difficulty to keep all of those things consistent with each other. So that's not perhaps, you know, requiring any kind of deep analysis, but just having a central repository of everything where many things are derived from the other things and keeping them all consistent is already a huge advantage. So I think that's kind of having the central safety model from which all of the artifacts are generated already provides a huge gain. So that's one advantage. But, you know, we're constantly being asked questions like, okay, so, you know, I have some, you know, autonomous vehicle and I need to do this much testing, and my testing is going to cost me so many $1 million. You know, how many $1 million, how many less tests do I need to run if I have a safety case? And unfortunately, that's a very, very kind of hard question to answer, and I'm not going to answer that today. And I'm often jealous of people in verification who are able to come up with very precise metrics that quantify, you know, progress over the years with their tools in terms of, you know, complexity of models and speed and false positives and so on. The trouble is with safety is that, you know, what we're interested in is, at the end of the day, is sort of safety events in the real world. And how on earth can you possibly quantify? You know, you can't do a kind of a double-blind experiment where you build one power plant with a safety case and another without it. And you see how many, you know, explode, or it's just very, very hard. And, you know, nobody has yet figured out a good way of doing this. So, you know, I mean, I'm really making an excuse here, but, you know, I acknowledge this is a very important question, but I don't have a very good answer to that, unfortunately. Okay.
Thanks, but I think those were elements of a good answer. So thanks. All right. Last minute question, anyone? Otherwise, I think we'll wrap up. No. All right.
Please send my slides around, over.
Sorry?
You can send the slides around.
Thanks, I will. Okay, so I'll stop sharing here. Thanks, Ewen, for bravely bridging the Atlantic over Hangouts through my computer. So, okay, thanks.
All right. Bye then.
Bye.
All right, guys. It is 1 minute past 4. That was our last presentation. So the only thing left is basically the closure and goodbye. We have a super quick poll at the end. So maybe Sina, you will help me out here. So just really quick, did you learn something new, and how would you rate the presentations? Obviously, we had some difficulties. Everybody seems to have learned something today, and we have no one saying completely irrelevant presentations. So I'm happy with that. With that, I think I will say thanks for arranging this, to the people who are behind this event, and thanks to everybody who contributed today. And of course, thanks for tuning in, the participants. It was great that you lasted this long. It's always tricky online, but I think we did well today. So unless there are any comments or questions to the event overall, then I will say goodbye and thanks, and enjoy your afternoon. Bye-bye, guys.
Bye bye. Thanks.